In this lecture video, we're going to start looking at simple random sampling. Now let's first review some definitions. First, a population is the collection of all objects or entities under consideration and about which we would like to draw conclusions or inferences. Sampling units are disjoint, collectively exhaustive subsets of the population. Now, sampling units may correspond to the individual objects or members in the population, but they could also represent collections of objects. A frame is a list of sampling units. And then a sample is a collection of sampling units that have been drawn or selected from a frame or set of frames. All right, now let's think about finite populations. Consider a finite population consisting of capital N values, which we will denote by U1, U2, and so forth up to U sub cap N. Now notice that we're using the lowercase letter u to represent values in the population rather than x's or y's. I'm going to use x's or y's when I'm talking about values in a sample, but when I'm denoting values in the population like I am here, where I'm listing the entire population, I'm going to use the lowercase letter u. Now make sure that you distinguish between the lowercase letter u that I'm using here and the lowercase Greek letter mu that I've got here in the middle of the slide. So the lowercase u's here are different than this lowercase Greek letter mu. Now, a finite population such as this has characteristics that we'll be interested in, for example, the mean and the variance. And so for a finite population like this, the mean of that population is given by this expression, so this should be very familiar to it at this point. You'll recognize this as the average, all right? And so it's 1 over cap n being the size of the population, times the sum of the values in the population. So the sum of the u values, u sub k going from 1 to cap n, and we will denote the mean of this population using the usual notation, a lowercase Greek letter mu. Now, once we have the mean of the population, we can calculate the variance. You'll recall that the variance of a set of data can be described as the average squared deviation of the values in the set about the mean. And so that's what we have here. All right, so we have the mean right there. So this is an average squared deviation of each of the values in the population from the mean. So 1 over cap n times the sum k going from 1 up to cap n of the square of u sub k minus mu. And then we'll denote the population variance by sigma squared. Now in this course, our focus is going to be on making inferences about finite populations such as this, and in particular about population characteristics such as the population mean, the population variance, and we'll also look at population proportions and population totals as well. All right, so let's define what we mean by simple random sampling. Inferences will be based on a sample from the population. In this particular section, we will be investigating what is called simple random sampling. Now here's the definition. The process of selecting a sample of size little n at random and without replacement from a finite population of size cap n is in such a way that every possible sample of size little n has the same probability of being selected is called simple random sampling. A sample obtained in this manner is called a simple random sample. All right, so again, what are we saying here that constitutes simple random sampling? Well, when we're sampling from a finite population, we're sampling without replacement. All right, and we're doing this in such a way that every possible sample of size little n has the same chance or the same probability of being selected. And so if we've selected a sample from a finite population in this way, then we're using simple random sampling, and the sample that we thus obtain is called a simple random sample. Now note that this is different than the type of sampling that you were exposed to and that you used in your first methods class. We've been reviewing that type of sampling procedure in this course in a previous module, and that was called IID random sampling, independent and identically distributed random sampling. Now, that type of sampling is different than simple random sampling because with IID random sampling, you're sampling with replacement. But when we're conducting simple random sampling, we are sampling without replacement. Okay, so that's what differentiates simple random sampling from IID random sampling, the type of sampling that that your entire first statistical methods course was based upon. But now again, a very important characteristic and requirement for a sample to be a simple random sample is that the sample has to be obtained in such a way that every possible sample of size n, little n, has the same probability of being selected. Now let's look at an example. Consider the following population of values. So we have a very simple situation here. We've got a very small finite population containing 6 values: 10, 3, 18, 32, 15, 27. All right, and so in order to keep this set of examples manageable, we're going to have a very small population that we're going to be working with. Now, what we want to do is list every possible simple random sample of size little n equal to 2. Now, there are a couple questions. How many such samples are there? In other words, how many simple random samples of size 2 are there from this population? And what is the probability associated with each of those samples? Now, you may want to stop the video for a few moments and see if you can list all of the samples of size 2, simple random samples of size 2 that is, and come up with a way of figuring out how many simple random samples there are. All right, so I'm going to continue on, but again, you may want to stop the video, and then once you get that worked out, then restart the video and compare your work to what we get on the following page. Okay, so here are the simple randoms, well, the samples of size 2 taken with replacement from this population of 6 values. And let me kind of zoom in here. And let me see here. Okay, so you can see that we've listed 30 samples of size 2. These are the samples. Let me see here. All right. Since we're sampling without replacement, we're not able to get 10 on the first draw and a 10 on the second draw, right? If we've drawn a 10, then the other values that we could take, that we could select from the population would be 3, 18, 32, 15, and 27. So if we select a 10 on the first draw, then there are 5 other values that we could get for the second draw. Likewise, if we select 3 on the first draw, the first selection, then there are again 1, 2, 3, 4, 5 other values that could be selected for the second observation. And you see here that the same thing applies for each of the values in the population. If we select these values for the first observation, then there are going to be 5 other values that we could get for the second observation. So, because of that, there are 6 times 5, or 30 possible samples of size 2 taken without replacement from this population of 6 values. And so I've got those samples, all 30 of them listed here. All right, and again, the number of samples of size n equal to 2, selected without replacement from a population containing 6 members, is equal to, and here's a formula that will work, You may be familiar with this. You may remember this from your first methods class. This is capital N permute little n, and this is equal to capital N factorial divided by capital N minus little n factorial. In this case, it would be 6 factorial over 6 minus 2 factorial, or 6 factorial over 4 factorial, and that simplifies to 6 times 5, or 30. In general, and I could have included one more simplification here, in general this will be equal to capital N times capital N minus 1. All right, so in this case that would be 6 times 5, or 30. Now the second question was, if we're using simple random sampling, how many, or what is the probability associated with each of these samples? And by definition, simple random sampling is such that every possible sample of a given size has the same chance of being selected. So since there are 30 possible samples, or 30 samples, each of them has a probability of 1 over 30 of being selected. All right, now let's look at example 2. So consider selecting a single simple random sample of size little n equal to 2 from the population in the previous example. Use the results from that example to determine the following probabilities. And so what we want to find is the probability that in our sample of size 2 we get 10. The value 10 is in the sample. We also want the probability that 3 is in the sample, and so forth. So for each of the values in the population, it looks like I've got 1, 2, 3, 4, 5. I've got an extra line here. Let me fix that. So let's go back up and look at the results. And so we've got our 30 samples here. What is the probability that we get a sample that contains a 10? Well, we see because all of these samples are equally likely, to calculate that probability, all we have to do is count the number of samples that contain a 10 and then divide that number by 30. And so we see here that we've got 1, 2, 3, 4, 5 samples that have a 10. And then we continue on. Here's a sample with a 10, so that's 6, and then 7, 8, 9, and 10. All right, and so the probability that we select a sample that has that contains 10 is 10 over 30, or 1/3. The probability that we get a sample that contains a 3 is given by the number of samples that contain a 3 divided by 30. So I see I have one here. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, and so again, we have a probability of 10 over 30, or 1/3, for the probability that we get a 3. And so it turns out, as you can see, that each of these probabilities is equal to 1/3. Now, we have calculated these probabilities by relying on the list, having constructed the list of all possible samples of size 2 taken without replacement from this population, all right, all 30 of them. And then we just counted. We resulted to counting the number of samples that had the characteristic of interest. For example, the characteristic of containing a 10. All right, and so that is how we calculated all of these probabilities. But now we've got the next result is a nice theorem that we'll be able to utilize, and it'll enable us to calculate these kind of probabilities much more easily. And so we're going to call this Theorem 1. In simple random sampling, all members of the population have the same probability of being selected for inclusion in the sample. All right, let me read that again. In simple random sampling, all members of the population have the same probability of being selected for inclusion in the sample. This probability is equal to the ratio of the sample size to the population size, so little n over capital N. Now, let me just point something out. This theorem, this result, follows as a result of the definition, okay? But by itself, it is inadequate as a definition of the simple random sampling process. In other words, it is a necessary condition for simple random sampling, but it's not sufficient. It's not a sufficient condition for simple random sampling. So, if we were to say that we have selected now listen very carefully what I'm saying here. If we say that we have selected a sample from a population, we've selected a sample without replacement, and all we say is that the sample has been selected in such a way that each member of the population has the same probability of being selected for inclusion in the sample, that in and of itself is not enough for us to conclude that the sample is a simple random sample. Okay, because in order for a sample to be a simple random sample, every possible sample of that given sample size has to have the same probability. But that's not what this is saying. This is something different than that defining feature or characteristic of simple random sampling. So again, what this theorem is saying is that if we take a particular member of the population, if we consider a particular member of the population, then the probability that we get a hold of a sample, that we select a sample that contains that value from the population, that probability is little n over cap n. Okay, so just make sure that you understand the difference between the defining characteristic of a simple random sample and this particular result. Okay, so again, let's consider selecting a simple random sample of size little n equal to 2 from the population given in example 1. And now what we want to do in this example is use Theorem 1, this theorem that we just looked at, to determine the following probabilities given below. Now, do these probabilities agree with those computed previously in the previous example that we calculated using basic principles? All right, and so let's go back and review Theorem 1 real quick. And so it says that under simple random sampling, all members of the population have the same probability of being selected for inclusion in the sample. That probability is equal to little n over capital N, which is the ratio of the sample size to the population size. Okay, so what would be the probability then that we get a 10 in a sample? What would be the probability that we get a sample that contains 3? What would be the probability that we get a sample that contains 18, and so forth? So for each one of those, okay, if we apply Theorem 1, then the probability that a particular value is in the sample that we select, that probability is given by little n over capital N. All right, and so capital N is 6, little n is 2 in this case, and so each of these probabilities is equal to 2 over 6, and when we reduce that, we get 1/3 for each. And so we see that those are the same values for the probabilities that we got in the previous example, the difference being that in this case, we don't have to list out the population in order to calculate these probabilities. That's what we're saying here on this slide. The advantage of using Theorem 1 to determine these probabilities is that it obviates the need to list and inspect all possible samples. We don't need to list the samples, and then we don't need to go through and count, identify those samples that contain the value of interest and count those up. That process, is subject to error. And if you've got a large population, anything really bigger than the population that we're using here, the number of samples of a given size that you could possibly have is going to be quite large. And so it would really not be feasible to use that first approach that we utilized to calculate these probabilities. So this is much, much, much easier. All we have to do to find the probability that a given value is in the sample that we obtain is determine the sample size, determine the population size. Those will be known in many cases, and so we could calculate these probabilities very easily.